Good morning, friends. We are again here to discuss some new topic of our interest. Our new topic for today will be about the topic, because now we have produced projectiles using accelerators. We have the accelerator projectiles, so we can go to the nuclear reaction. So we are to talk about nuclear reactions because now we have the projectiles, accelerated particles, to start with the study of nucleus. So we have now nuclear probes. Nuclear probes, as I told you, are the radiations, the particles to be sent towards the nucleus to study the property of a nucleus. Property of nucleus means nuclear structure, nuclear constituents, and nuclear radius, etc. What do you mean by a nuclear reaction? How to define a nuclear reaction? Just like any reaction, chemical reaction or any other reaction. Well, some interactions to probe a nucleus, in which some radiations, some nuclear probes are sent towards a nucleus. And the interaction between the projectile. The projectile can be a single nucleon like neutron, proton, or it can be a combination of nucleon. It can be a neutral particle, neutron or gamma radiation. It can be heavy ion. It can be mesons, pi mesons, mu mesons, or heavy mesons. Any radiation. So when a projectile is sent towards a nucleus, towards a target having large number of nucleus. In a nucleus there are large number of nucleons. So what will happen? Remember, we are not concerned with the atomic electron. This is not the atomic. We want to study the interaction of projectile with the nucleus. So an interaction in which a projectile is sent towards a target having large number of nucleus, there is a transfer of energy momentum, because projectile has got energy momentum. So when a projectile interacts with the nucleus or the nucleus of nucleus, so interaction between a nucleon or a combination of nucleon means more than a nucleon. Interaction between a combination of nucleon with a nucleus as a whole or nucleon, in which large number of energy, large number of nucleons transfer is possible, that is large number of mass transfer is possible, or it is possible to have momentum transfer, it is possible to have energy transfer. So interaction in which a nucleon or a combination of nucleon is sent towards the nucleus having large number of nucleons, there may be transfer of energy, there may be transfer of momentum, there may be transfer of mass, that is the nucleon. So such an interaction in which there is involvement of nuclear forces, involvement of nucleus, involvement of nucleons is known as the nuclear reaction. So interaction between projectile and a nucleus, projectile may be combination of nucleon. The interaction between projectile, combination of nucleon, interaction between a nucleon or more nucleon with a single nucleon or more nucleon or as a whole, nucleus as a whole is known as nuclear reaction, in which there is a transfer of mass, there is a transfer of energy, there is a transfer of momentum, etc. So such type of interactions are called nuclear reactions. I can have some example of nuclear reactions and the type of the nuclear reaction. There are the type of nuclear reaction. One is known as the elastic scattering. elastic scattering means scattering in which there is no appreciable energy transfer. It is not 100% correct to say. If we ask anybody what is the elastic interaction, they say always that when there is no energy transfer, energy remains same. So no energy loss. Or simply they say interaction where there is no energy loss, there is no energy. Elastic. Interaction where there is energy loss, there is no energy. Inelastic. So there are two types of interactions. One is elastic, other is inelastic. So what is the difference in the elastic and inelastic? My definition for elastic interaction is the interaction where there is no appreciable energy loss. What does it mean? It means that there is energy loss in elastic also, but it is not appreciable. There is energy loss which is required to conserve the linear momentum, because linear momentum is conserved in all interactions. So interaction in which there is no appreciable energy loss, and I say more accurately, in which the initial system and final system both remain in the initial quantum mechanical states. That interaction is known as the elastic. The system remains in the same initial quantum mechanical state. Means there is no excitation of the system. There is no excitation loss. Inelastic scattering is in which the target nucleus remains in the ground state. There is no excitation. There is no appreciable energy loss. If appreciable energy loss, system will go in the excited state. Some energy loss is there which is required to conserve the linear momentum. When linear momentum is conserved, there will recoil. When the interaction taking place, the recoil goes. So when momentum is conserved, some energy goes to the system in the conservation of momentum. And that energy is very, very small. Say energy loss, momentum is P, then P square over 2m, where m is the mass of the system, m is very large. So energy will be very small, P square over 2m. So energy loss is there. So remember, clear definition, understanding that in the elastic collisions, there is also some energy loss, but we neglect that because it is not appreciable, it is very, very small. It is P square over 2m, where 2m, m is the mass of nucleus, very heavy. Projectile, P momentum is very small. Because the projectile is a very small mass, mv is the momentum. So P is very small, m is very large, and hence energy, recoil energy loss is there, that will be very small. So elastic scattering, we can say no elastic scattering, where we can say that no appreciable energy loss. And in elastic, of course, obvious, there is energy loss. Well, now I will give some example to you that say interaction of energy loss, or that means I say interactions which are say some example of elastic. I represent a reaction, a nuclear reaction. Is represented as x plus x plus x. This the x is projectile. This is the target nucleus. So projectile small x plus capital X target nucleus, we get after the interaction also x plus x. This is the elastic. Because there is no energy loss. Energy loss is there but we cannot show, it is not appreciable, it is only required to conserve the linear momentum. So elastic, there is change of direction. Change of direction of projectile. And x, I write again x plus x. And if I get here x star plus x, this x is of reduced energy. X plus x, x star plus x. This x star is now, this x is of reduced energy. So x has taken some energy. X star is excited. Excited state. And hence x star goes to the ground state x plus emits a radiation gamma ray. By this collision, x takes some energy from a small x projectile. This projectile is of reduced energy and x goes to excited state. And it cannot remain excited state. It is unstable. It is having lifetime. So this x star comes to the ground state and this x and the difference of energy is emitted as the gamma rays, electromagnetic radiation. So this is inelastic in which energy loss is there. Now I can give you some more example of reactions and some more details. Let me write some more details of the reaction and giving examples. So what are the, say, types of, I can have types of nuclear reactions. What the meaning of types of nuclear reaction? Means I have discussed elastic and inelastic. That is not all. So what are the types of nuclear reaction we have? The types means how many types, how many different nuclear reactions are there. So I will give you some example. I have given you example of elastic scattering. I write say types of means when I give you elastic scattering, I again write and give some example. Example is say I give x plus x. I can give any specific example. That is say I have alpha particle, 2 helium-4. This is alpha particle. 2 helium-4 strikes with 79 volt, 197. This I get here after interaction 79 volt, that is 197, plus 2 helium-4, that is alpha particle. Alpha particle means doubly ionized helium atom. It is doubly ionized helium atom. That is alpha particle. So this is elastic. And now I give example of, say, inelastic. Inelastic example. I can give you an example of inelastic, and that is I take some projectile side take proton. Proton means hydrogen which is ionized, means plus point charge. So that is proton. 1H1 is striking with say 3 lithium 7, which is the target. What happens? Lithium 7, 3 lithium 7 goes to excited state, star, plus 1H1, that is reduced energy. So this is now 3 lithium 7 in the excited state. The 3 lithium 7 can come to ground state of 3 lithium 7 emitting a gamma ray. This is a specific example of elastic and inelastic. Now another example I have here. Now some reactions are say 1, 2 and say 3 means one specific reaction I am giving you, that is photo disintegration. What is photo disintegration? Means disintegration of a nucleus by photon. That is, photon means gamma radiation. So photo disintegration, I have say a gamma ray is the projectile, and I have here 1H2, that is the heavy hydrogen, means deuterium. Deuterium as the gas, as the target. Gamma ray interacts with this, what we get? Gamma ray interacts with this, we get, oh this is here, reaction. Gamma rays interact with the, so photo disintegration means disintegration of this deuterium or heavy hydrogen. What we get after disintegration? We get after disintegration 1H1, that is the simple hydrogen plus a neutron. So this is a specific reaction, the disintegration of, and this is used, this is the use for the production of neutron. If you want to produce neutrons in our laboratory, we can use gamma ray. Gamma ray source, strong gamma ray source of some long lifetime, and we can use the deuterium target and we bombard this by gamma ray. We get neutron beam. So depending upon the gamma ray energy, neutron will have kinetic energy. So this is the disintegration of the nucleus to produce neutron. Now we have say example of what we say, some number 4 or 5, I don't know what number. I have say disintegration, simple disintegration. Earlier we took a special example of photo disintegration. Now this is example of simple disintegration. Means a system is disintegrated. Means I have a projectile X, I have a target X. This disintegrates. Means this becomes X plus X, means C, where C is what? X plus X. So this enters this is captured by this, a new system is formed. This C is called a compound system. And this C can break now into components, different parts. C breaks now, we get say Y plus Y. or Y1 plus Y1. This may break into different components depending upon the mass of C. It can be a combination of Y2 plus small y2 or y3 plus y3 and so on. This the disintegrations into different means this can be different combinations, different systems, different outgoing parts. These are emitted particles, and these are residual nuclei. What remains after disintegration? Residual nucleus and emitted particles. This can be different combinations. Or it is also possible that multi-particle, I will give example later on, but simple example I can write for disintegration. Suppose a reaction is where I have alpha particle, that is twice helium-4, WIR. I have the alpha particle and I take this alpha particle and I take any nucleus, alpha particle plus, I take a target nucleus, say 7 nitrogen 14. What I get? Alpha particle is 2 helium-4. So this is now absorbed there, and after absorption means 7 plus 2, 9, 14 plus 4, 8. So this becomes 9. 9 is fluorine. And this is 14, 18. So compound system is fluorine, 9 fluorine having 18 mass. This is compound system. This may break into different components. One of the components I can write here is simply, this breaks into 8 oxygen 17. Charge becomes 1 less, so this becomes 1 charge here. Mass becomes 1 less, so this becomes 1 charge, 1 mass, proton. Proton is emitted. 8 oxygen 17, after this is disintegrating into this and this. So this is one example. Like that there can be say different disintegration means this system can be different combination. This can be 7, then there are 2 charge. This can be mass may be 16, then it must be more, 2 mass here. Like that. So disintegration into different components is possible. So these reactions are known as disintegration reaction. So these are types of reaction. I can have another type of reaction. What is that? I have said radiative capture. This was capture also, you can say. Disintegration means capture. After capture we get compound nucleus and then it decays, disintegration. I have now say radiative capture. Radiative capture is a capture of target and that is the projectile into target where the decay system is not a particle, only gamma ray. So radiative means emission of a capture of projectile where there is no emission of particle, disintegration into gamma ray and remaining system. So that example, radiative capture, I can give you say 12 magnesium 24 plus I have some proton. This proton is captured and we get a compound system of 13 aluminum, magnesium, 13 aluminum and 25. Remember that this projectile will give energy. So this system is always excited state. Compound nucleus is always excited. Only then it can decay. So this excited state. This is radiative capture means 13 aluminum decays into the Sorry. This is, 24. This is magnesium, sorry, not 24, magnesium 26. Magnesium 26 captured when this is 27. So formation of aluminum is 27. So this is now formed 13 aluminum 27 plus gamma. So this is radiation. Or gamma radiation. So this is capture of proton by target nucleus to get a excited state of compound nucleus. This decays by emission of a radiation only, no other particle. And this system comes from excited to ground state. So this is known as the radiative capture. Capture of the type where gamma ray is emitted only. So this special name given here is radiative capture. We can have some other reactions. These reactions are mostly at lower energy, these are at high energy. High energy like 2 MeV. So these reactions are called direct reactions. I will explain you later on the direct and compound reactions. So direct reactions are reactions. Example I give you, say 29 copper 63 plus I have projectile 1 H2. That means neutron. Now this, what we get from this? The neutron has 1 proton, 1 neutron. So there are 2 mass. And this captures 1 nucleon from this. It becomes 29 copper 64. 63, 64. Mass charge is not. Charge remains. So it is now, it becomes a 1H1. So this is direct action. If neutron beam hits the copper target, we get copper 64 and this is a proton is left. So what we have done, from the deuterium we have taken 1 nucleon. Such types of reactions, direct, they are called stripping reactions. Stripping reaction means you have taken something, stripped off. The neutron is stripped off 1 nucleon. You removed 1 nucleon, removed, and this reaction, say, like example, you say that this was the target, say, copper 63, like this, and this beam was coming. This was 1H2. And here beam is going and inside this, and then this particle is going. This 1H1 or proton, you can say proton is going, and here this absorbed is the neutron. Neutron is absorbed and proton is emitted. It is also possible that reverse may also be possible. What reverse is possible? That proton is absorbed and neutron is going. Proton is absorbed and neutron is going. Means such reactions are also possible. This reaction is known as, say, what we call DP reaction. Neutron is, this is the neutron. Neutron is going and proton is emitted and neutron is absorbed. So this is DP reaction. We can also have DN reaction. I don't give any specific example. I can simply write in terms of say X plus X is equal to Y plus proton, or X plus X is equal to Z plus neutron. Means here from the X, this means or X we can write 1s2 directly D 1s2. That is the neutron and neutron. So neutron here, neutron is absorbed, proton emitted. Here, proton is emitted, neutron is emitted. Like that. The reactions are proton is going, here neutron is coming, X is there, and here the neutron is absent. This. And here the neutron is coming, and this neutron is going, and proton is absorbed, X, which is the neutron. So neutron is coming, proton is absorbed, neutron emitted. And so this is stripping. This is also a stripping reaction. Means you are taking something from this projectile. The projectile is stripped of something. So these are stripping reactions and these are direct. They are inverse of this also. Means this is stripping, we can have pickup. The pickup reactions are like that. Say proton is coming and X is there, and here we get say Y plus neutron. Means proton picks a neutron from here and it converts into neutron, and remaining system is Y. Means this was the system say X, and here the proton was coming and it takes a neutron from here, and a neutron is taken from here and it goes as the neutron. So picking, this is pickup reaction, means picking up a neutron from the target and this proton converts into neutron. Or you can have a proton interacting with X, in which we get some new system Z, and plus here what we get? This is neutron emitter, so here also neutron emitter, but this is a proton is coming here and X was there, and this goes as neutron. Oh, sorry. This is the same thing, neutron. I should have here a neutron. A neutron is coming and neutron is here. A neutron is coming and it picks up a proton and it becomes neutron. So reactions starting from proton and target X, in which Y is residual system and neutron is emitted particle. Proton is coming, it takes neutron, it picks a neutron from the target system and neutron is emitted. Here, neutron is coming, it takes a proton from the target system and a neutron is emitted. So these are the pickup and stripping reactions. We have stripping, this is stripping, and this is pickup. But these are stripping and pickup reactions are at higher energy. So these reactions are possible, and these are called direct because there is no formation of compound nuclear. So these are also direct reactions. Now I can give you some example of, say, these direct reactions are here induced by the neutron and proton or deuteron stripping reactions. Similarly, direct reactions are also possible under the heading of direct reactions. We can have, say, heavy ion reactions. Means in place of light ion like alpha particle proton, you have the heavy ion. Suppose I have an ion of nitrogen. This is the projectile. And this interacts with the target of, say, heavy target means lead, PB 207, it is 82. So this interaction in which we get this nitrogen 14 becomes nitrogen 13, and this is here 82 PB, what? 82 PB 208 from 207. It means from this a neutron is taken. Means nitrogen 14 is stripped of a neutron. So this is also a stripping reaction. Heavy ion earlier was light ion like deuteron stripping reaction. This is the stripping reaction introduced by heavy ion, nitrogen 14. It is charged state, maybe 4 state or 3 state, whatever. So this 7 nitrogen 14 energetic particle, that means it is ionized. So ionized nitrogen as the heavy ion beam strikes with the PV and it goes as 7 nitrogen 13 and something means a neutron is taken from it, stripped off, and we get new system. So this is the example possible, other also possible where a proton is taken. And now I have another important reaction which you have said for the nuclear energy purposes, that is the fission. Nuclear fission is the example of energy purpose reaction, or some number maybe 7 or 8, whatever. So I have said or 8 nuclear fission. What is nuclear fission? Well, nuclear fission is spallation reaction. Fission of heavy system into light system. Like we have 92 uranium 235 and we have, say here, a neutron. What we get here? We get here 40 zirconium 98, 40 zirconium 98, and we get 52 tellurium 136 plus 235, 236, this is 234 plus twice of neutron plus of course energy. So this is a reaction which is nuclear fission, in which a heavy system like uranium, this neutron initiates the reaction with uranium, we get combination. These can be different combinations. All different medium weight nuclei, you can combine with different. This can be 41 or this can be 39, this can be 45 and remaining like that. So these two can be different sharing, but medium weight nuclei. And remember, neutron was one is here and we get 2 neutron after interaction. So this is the beauty of this reaction, fission, that fission reaction, neutron is fissioning a heavy nucleus into light nuclei, and we are getting more neutron. So it means we started 1 neutron, we get 2 neutron or 3 neutron, depending upon this combination. So means more neutron than the initial, and this is called chain reaction, in which we get more neutron, and these more neutron start the reaction with this system again, and we get again more neutron. So a chain of these system and neutrons is produced, and this chain is used like the energy source. Means if it is not controlled, it becomes atomic bomb. If it is controlled, it becomes nuclear reactor. So nuclear reactor is the control device of fission, where we use this fission reaction to produce energy, and that energy, heat energy, is used to boil the water to make the steam, and steam is used to move the turbines, and turbines rotate, say, motors just like dynamos, and electricity is produced. So in hydropower we have waterfall to move turbines. In this we have steam to move turbines. Steam, the nuclear fission is used only to produce heat energy that boils the water. So near the reactor we should have source of water also. So all reactors are nearby some rivers or source of water. So this fission is used to produce electricity, is used to produce an uncontrolled way atomic bomb. This is the fission reaction or nuclear spallation reaction. Okay? Now we will talk about something more. We go further and we talk about, say, how to get the idea of we define a parameter known as reaction cross section. So what the reaction cross section? How to define reaction cross section? What is reaction cross section? Yes. Any idea? What is reaction cross section? How we define? So reaction cross section, it is the measure of amount of the reaction. Means how much reaction is taking place. What is the reaction taking place? Means it is the probability of reaction. What is the probability of reaction? How much reaction? How much more? How much less? So how we measure the reaction? You see, what is the reaction? We have reaction in which we have, say, a projectile, means incident particle, and we get, after interaction, some number of particles, emitted particles. We have target nucleus, for which the nucleons of the target nucleus or nucleus as a whole interact with the projectile, and they are emitted particles. So we can have the probability of the reaction. I will try to define some language. We can say that number of particular events produced number of particular events produced. Events means per unit time, of course. Events unit time. Per nuclei. Number of events produced per unit time You can say events, time is included, but I can write per unit time. Number of particular events means number of particular outgoing events. Events going out, outgoing events, divided by number of incident particles per unit time. That will be event per unit time. That and per unit area. Per nuclei. This is the measure of probability, measure of reaction, probability. We write this by sigma. Sigma. Sigma is known as the nuclear reaction cross section. Reaction cross section. Sigma is the probability of reaction. What is that? Number of particular types of events that are outgoing per unit time and divide by how much particles were coming. Number of incident particles per unit time per unit area. This is called flux. Flux of the particle. Per nuclei means in the target there are so many nuclei. So per nuclei. How many nuclei, how many nucleus are present there in the target nucleus. So this gives the measurement of. But how much particles were coming, how many particles going out, what is the outcome, what was the input. Input was number of particles striking in the target nucleus. Per nucleus, how many particles are produced per unit time, per unit time. So this is the events and this is the flux of the particles and this is the nucleus in the target. So this is the theoretical, some just language definition or idea what the nuclear reaction is. Reaction cross section, what is the probability of nuclear reaction. Well, how we write this mathematically? We can write this also mathematically. Say, what is the nuclear reaction cross section? Say, nuclear reaction cross section. What we write? What is the number of events nuclei produced? Number of events of nuclei produced. We write, say, suppose delta. Suppose events produced are, say, delta n are the events produced. Means number of radioactive nuclei produced, delta n. Then this is proportional to what? Delta n is proportional to what? N upon S. What the N and what the S? Into we write, say, N S delta X. What the interpretation of different thing? Say, N is number of nuclei per unit volume of the target. S is target area. Delta X is target thickness. we have a target which the reaction is going on, means a target of some this is the thickness of target and delta x. And here in this system n number of nuclei in the unit volume and S is the target area. S is the target area. This beam is coming like this. So beam is striking a target having thickness delta x and S area of the target n per unit volume, number of nuclei per unit volume. And what else is left? So n S delta x and n capital N and is what n? Number of incident particles per unit time. That is the beam coming. How many particles? Incident particles coming. And delta and events produced is also per unit time. Whatever time this, same time. Or you can divide by time, then they divide by time. So this is the events produced, or we can write the event produced, how we can write? The event produced delta n is proportional to this or equal to sigma constant of proportionality n over s and n s delta x. So this sigma is constant proportionality of proportional. We write sigma s delta n, that is events produced. We can write by any other symbol, delta n, and s is cancelled. Delta n divided by capital N and n delta x. So this is, you can say, mathematical expression of sigma, or we write here, say, divide by s here, and then we write s also. That means number of particles, flux per unit time per unit area, and these are n delta x as number of delta x s is the area and n is the volume. So this becomes n into volume. This is per unit volume, volume cancel. So this becomes finally n number of nuclei. So this becomes simply number of nuclei. Now see my language definition of sigma earlier which I gave you. What was that? And see that. Sigma is the cross-section of the probability of action where I wrote number of events per unit time. Number of events per unit time. This is number of nuclei and this is number of incident particles per unit area per nuclei. So this mathematical equation is same as I wrote earlier in the language. The probability of a nuclear reaction is defined as number of events per of particular type per unit time, this is per unit time, and divide by number of incident particles per unit time per unit area per nuclei. So this mathematical relation and my earlier theoretical definition, both are now same, and that gives you the measurement of nuclear reaction probability. we can also write that same expression, like say, we can also write that sigma is equal to cross section is equal to sigma is equal to d and dt per unit time divided by n, or what you have, and n is coming here. So we write some other symbol. We write some other symbol, say phi, and say per unit area and number of nuclei. So this see, sigma is a d and dt means also this called disintegration rate. That means number of events per unit time means the radioactivity produced, how it is disintegrating in unit time. That is the method of events. And phi over s means flux, that is per unit time, per unit area. And this is number of nuclei. So from this is simply number, time here, time gets cancelled, and this s. So sigma has now dimensions of area, because this is number of nuclei, number. This is the flux number, this is the area here, and this is per unit time, of course, time is also here, and this is also per unit time. So everything is cancelled, but we get this s numerator. So sigma has dimensions of area. That is why it is called cross section, reaction cross section. Reaction cross section because it has dimension of cross section area. So its dimensions are dimensions of area. So it is a term, otherwise it is probability of reaction. It's more value, more probability, less value, less probability. How more value? More value means more outcome, more events produced. Less event means less probability, so less cross section. So sigma is the measure of the probability of the reaction, and just using this type of formula we can measure this experimentally. So how we can measure the cross section experimentally? The measurement of sigma experimentally. How we do measurement? For the measurement of sigma, what we do? Using this formula. One, I will explain another formula to you. This is one formula, so using this formula, I will explain you how to measure. Means you measure the d and dt, measure outgoing events, means d and dt. So what the events are produced by some detector, using some radiation detectors, gamma ray, particle detector, you measure the disintegration rate, means radioactivity produced, how it is decaying. So that gives you event produced by the reaction. So you measure experimentally outgoing events by using some detector. Means you have a beam of the particles, you put a target here, and then this is in some chamber, and then the events are produced here. So these events are produced, detector. And these are the particles, the beam. You know this flux. Flux is measured by flux meter. Flux can be measured by current of the ions also. So this beam is flux is known, means this thing is known. Flux, number of incoming particles per unit time, per unit area. That is the flux of the particle. And you know the outgoing beam by detector here. You measure d and dt. And then number of nuclei you calculate from the target. Target number of nuclei, you can calculate number of nuclei. Let us say M N F over K. The mass of the target, N is the Avogadro number, F is the isotopic abundance, and A is the atomic weight. A is the atomic weight. N is the Avogadro number. F is isotopic abundance. Means how much abundance of this mass, this atomic weight, this isotope is 90%, 50%, 30%. So that percentage F is a fraction. 90% so 0.9, 30% 0.3. So F is the isotopic abundance of this material. M is the mass of the sample target. So using this we get number of nuclei. So we know number of nuclei. We know the flux by measurement of current. Direct you can measure the current by the flux meter, or you measure the current by Faraday cup. The accelerator we have at the end of the system, target we have a Faraday cup, which gets the total charge collected. And that total charge gives you current, and that current can give you number of protons or number of alpha particles, whatever. From charge you can calculate how many particles are there, because you know charge of one particle. So that gives you flux. And dNdt is measured by some detector, useful detector for that particular radiation. It may be ion, it may be proton, it may be particle, or it may be gamma ray also. So you can use the gamma ray detector. So whatever detector used, by using this relation, you can measure sigma x over G. Remember here for measurement of sigma, there are two types of arrangements, two types of experiments are there. One is known as the off-beam experiment, and other is the on-beam experiment. Means you are making the radioactivity by bombarding it with your target, and you get that radioactivity. Radioactivity is disintegrating, giving you beta decay or alpha or any other decay, whatever. So we are getting some radioactive product from which beta gamma radiations are coming out. So you measure, you do the experiment, produce some activity in the target, put the beam off, remove the target, and bring this target to the detecting system and count the radiation, that is gamma or beta particle, whatever you are interested in, mostly gamma. So count the gamma using SPE detector. Off beam. Other is on beam, when your beam is also on and you are putting the target there and you are sitting in the control room. From there you are watching your target also, and you are getting the radiations detected because detector is there inside, and you are sitting in the control room where your multi-channel analyzer and our electronics unit is there. You are getting the pulses counted there, but detector must be inside. So detector is inside, and continuously the beam is hitting the target, and you are getting continuous events, and you are measuring by the using the electronics multi-channel analyzer. So you get two types. Off beam you do in your laboratory, you take the sample in your laboratory and count there by putting the accelerator off, and on beam the accelerator is not off, it is continuously bombarding the target, and you are counting the on line or on beam radiations coming out. So these two types of experiments are performed, and in our country, India, we have at the Delhi IUAC, Inter-University Accelerator Center, and at the Kolkata Cyclotron, Tata Institute, Bombay, Mumbai, we have TIFR, Accelerator, Pelectron there, and some small, and now not working, small cyclotron of IMB at the Chandigarh, and all others were small cockroach finished now. Bandigraph, no bandigraph now. Earlier bandigraph was at Tata Institute working, now it is not working. It is donated to some Calicut University, probably Kerala, and no other. We have only tandem working tandem at Delhi and Mumbai, Tata Institute, where we can use this type of experiment. And we have been doing since long, and still our group are doing this experiment, and so many other persons from different universities are working using the same accelerator in the university center. That is, we work there, and we can study the nuclear reactions of various types of your interest by on-beam experiment and by off-beam experiment. Good. So, friends, I will stop today here. Next time, maybe tomorrow when I come, I will discuss something else, or I will continue from this point. I will explain some other experiment, another method of measurement of perception, and then I will go to some theory. So thank you very much for listening to me.